Great, so we're back. Um, Now we've learned about the central limit theorem and we had the law of large numbers, and now we can put things together to go the other way. What I mean is, so far we always said we've got a population, we've got a model, and kind of that explains how we get the sample. But now we're thinking we only have a sample, that's all we've got, an n sample, and can we make estimates about what the population would be like, yeah, in the absence of any further knowledge. So if we don't know whether it's a fair die or like another system that spits out numbers with a different distribution, we only have the sample of 1, 3, 4, 4. And given that, we can, make assumptions about what model might be behind the whole thing. So that's what we want to talk about first. So what do? We only got this sample, and now we are supposed to come up with a model that has an expectation value and a variance. And obviously the expectation value mu, the best estimate for that is just the mean value we have. Yeah, that's the best we can do. In absence of further information, we can't calculate anymore. How about the variance? Well, we've got the sample variance. So, yeah, that's our best guess. So we just take those two numbers and plug them in. So graphically speaking, we assume our population, our model has those properties here. Now, what we know is, our sample is one of many possible samples. There could have been sample 2 and 3, and all have like different mean values, different sample variances, and obviously there's going to be a bit of a variation in here. And our question is now, I've made all my assumptions based on sample 1. Yeah, that's all in our so I said like mu is here, but in reality mu is here. Yeah, we know we're always going to have a little bit of an error, and I said like, oh, maybe my sigma, my variance is this, but in reality it's different. It's more like this. So how reliable are our estimates? We know from the law of large numbers that if we go to really large samples, our estimates are going to be better and better. But do we know how good they are? Can we quantify that? And that is the kind of the topic of this lecture, of this video. And we can use the standard error. We know that these mean values that we calculate, so my x here, that is according to the central limit theorem, that is normally distributed, and it has a variance of sigma squared over n. So we know the mean values. If I put all those mean values here, up here, and I do that with lots of samples, then those sample means have a distribution of their own. This is the distribution of sample means. And it is more narrow than the distribution of the random variable itself. Yeah, the random variable, this is the kind of distribution of my random variable, but the sample means, they have this factor 1 over n in them. Yeah, so it's a lot tighter, it's a lot more narrow, and that gives us kind of some confidence intervals, and that kind of gives us the information how reliable we are. So this is the idea of the whole thing. Now one little problem is I've got sigma squared in here, and that's the one value we don't know. Yeah, so in order to guess the distribution of sample means, I need the variance of my population, which I don't have. So we have to go even one step further. We have to say, okay, I've used my sample variance to guess my population variance, and I've used my sample mean to guess my population expectation value. Now if we want the variation of sample means, the standard error, then if we don't know sigma squared for real, we have to take my sample standard deviation. Yeah, we have to use s squared. And obviously that's going to incur an additional uncertainty, an additional error, but we can take that into account and won't be like a big problem. And we'll see this error isn't that big for like samples of a decent size. There's not that much of a difference. So here we go. Here's what we've had before. So if we know the population standard deviation sigma, then everything's good. This is what we had before from the central limit theorem. So the sample means they're normal distributed with expectation value mu and a variance of sigma squared over n, meaning the probability that a sample mean is smaller than a given number is just given by the cumulative distribution function by our phi of a minus mu over sigma divided by square root of n. Yeah. So we can use our standard normal distribution to calculate all probabilities about the sample means. Brilliant. So now what happens if we have to estimate the population standard deviation with the sample standard deviation? And what we haven't looked at is what the distribution for that is. It's a chi-squared distribution. Yeah, s squared, the sample variance, is chi-squared distributed. A chi-squared distribution. It's another one of the important distributions, but for us it's not that relevant, so I left it out. Have a look online or in books if you're interested. There's quite a lot of interesting things you can do with chi-squared, but basically we're just gonna use it. So what happens if we have something that's chi-squared distributed inside something that's normal distributed? Then the result of this is a student t distribution. Student t distribution. That is basically, if you take the normal distribution and the chi-square and put them together. Yeah, those two combined. And it has this number n minus 1, the degrees of freedom, which is basically the sample size minus 1 for our purposes. The name student T, by the way, in funny story, it's Irish mathematician who was working for the Guinness factory, in fact, and he wasn't allowed to publish under his own name. So his company said he has to publish it under an alias name, so that was his alias, and it's remained under that name up till now. Okay, so let's have a look at the student T distribution. So here in yellow you see the normal distribution. Yeah, that's what we would find if we know the variance, the population variance exactly. And if you don't know it, if you introduce this additional insecurity through the chi-square distribution of our sample variances, then the distribution just becomes a little bit wider. You see, that's like not as high, and here on the sides, yeah, you get further out. So basically this accounts for the additional uncertainty. We're not as certain for our guess. This is just for 1 degree of freedom, so yeah, no wonder sample of 2. If you go to a sample of 9, k equals 8, then you see that student T is already pretty similar to the Gaussian distribution, to the standard normal. And if I go to large number 20, they're almost identical, at least visually. So for our purposes, there won't be any need to work with the student T distribution. We're just gonna stay with the normal distribution. Yeah, that's good enough for our purposes. Okay, let's do a little exercise. So it's been a lot of new concepts, a lot of new things I told you. So now it's your turn. What is the standard error, the standard deviation of the sample mean for rolling a fair die 10 times? And I've given you the individual values already. Excellent, yeah. That one wasn't too hard, there was a little warm-up. So basically the standard error is just the standard deviation divided by n squared. So n is 10, so divide by square root of 10. In your calculator you get 0.54. So it's like, roughly speaking, 3 times more narrow, this distribution, than the individual random variable. Okay, different question. Now we've got this data set. So you roll the die 10 times. This is the outcome. And now I'm asking, how likely is it that you got this 10th sample from a fair die? And you will need the sample mean and the normal distribution for this one. Okay, good. So let's have a look at this. So you've all probably calculated from this one here that the sample mean, here we've got it, the sample mean is 4.1. And for fair die, we know we'd expect 3.5. So there's a difference of 0.6. Now, we know a standard error is 0.54. That's what we just calculated. So this is basically the standard deviation of our sample means, like the one we have here. So what are the chances that our sample mean is out by 0.6 when the standard deviation of sample means is 0.54? We take the difference, 0.6 divided by this 0.6 divided by 0.54, and that gives us this term. I've just used the symmetry of the normal distribution again. So I just look up normal distribution, cumulative normal distribution function at the point minus 1.1, and that gives me a 14% chance. 14%. So that means 1 in 7 sort of chance that we got a sample like this one above just randomly. It's not too unlikely. So as always in statistics, you have to find a hurdle. You have to find a value where you say okay, this is my distinction, I believe it up to that point. So it's not black or white. The going practice often is to use 5% hurdles, but it depends a bit on the field and what you're working to. So I guess 14%, we could still argue, okay, it's conceivable that this sample just happened by chance. It wouldn't be too weird. Okay, let's do another sample. It's basically the same task, but I've given you a different sample here. How likely is it that we get this sample from a fair die? Exactly. Well done. So again, I calculate the sample mean. Sample mean is 2.4, so quite low. I've got a lot of ones in there, as you can see. Expectation value was 3.5, so we're out by 1.1. 1.1 away from the expectation value with this standard error. So again, we'll divide the difference by the standard error, and we look up normal distribution. Two standard errors out we are. Two standard errors out. I can use my table. This is the normal distribution table, and I get 2%. And now most of you will probably be thinking, oh, that's only 1 in a 40, 1 in a 50 chance to get this sample. I mean, it's not impossible, nothing's ever impossible, but it's starting to be quite unlikely. So we could be tempted to say chances are good, it's not a fair die. Yeah, this is how this goes. Obviously now we always use the kind of this value here, the sigma that we had from a fair die. If we only had the sample and didn't know anything else, we could also use the table of a student t distribution here on the left, but numbers aren't that different and the concepts stay the same. Cool. Well done, everyone. So in the next video, we're gonna kind of swing the, basically we're gonna do the same thing, but we're just gonna swing the question a little bit round and say what is the interval in which these mean values can lie, where we're still confident that things are all right, and when are we starting to be worried that something's not as expected. All right, see you in a sec.